5 kilometers just one day. And one feature of space-time curvature is also that it becomes stronger when a certain mass is compressed to a smaller size. So if we had some way to crush the Earth to smaller and smaller size, the curvature would get stronger and stronger. And this would continue kind of smoothly for some time, but eventually it reaches a critical limit when something very dramatic happens to the space-time and a black hole forms. And for the Earth, this is about the size of a large grape or so. And as you already heard in the excellent talks this morning, a black hole is a very unusual entity. It has no surface, only an event horizon, which is a barrier for any information that an outside observer can have about its interior. And near the horizon, space is strongly curved, time flows slower and slower compared to an observer at large distances. And also if the black hole is rotating, it actually drags the space around it into a whirling motion. So lots of interesting effects. But one thing to also note is that from the outside and from kind of larger distances, a black hole is actually kind of a perfect and very elegantly simple type of object, in the sense that it is entirely characterized by just two quantities, namely its mass and its spin, how fast it rotates. And this is very different than an object like the Earth, where you also have to know where the mountains are, where the glaciers are distributed, and the oceans and so on. So for an object like the Earth, you would need many more parameters to characterize it from the exterior. So clearly many interesting features of space-time curvature, but what I've described so far was completely stationary situations. But now it is not a far stretch of the imagination to think about what happens when masses are actually accelerating. So then we would expect that they should create some dynamical distortions in the space-time. And this is exactly the case. And far away from the source, one sees these dynamical distortions in the space-time curvature as kind of ripples, but in the fabric of space-time, which is hard to visualize. So we resort to these kinds of lower dimensional animations. But these are the gravitational waves. And they have many interesting properties. For example, it takes a huge amount of energy to create even a tiny wave in the space-time. So in everyday motions, we create completely negligible amounts of gravitational waves. It really takes some violent events where huge masses are moving at extremely high velocities with very large asymmetries to create a noticeable gravitational wave. And related to that is also a feature that gravitational waves interact very weakly with matter. So on the one hand, that is really great because it means they can travel through the densest and most dynamical regions of the universe, almost uncontaminated by any kinds of absorption, attenuation, or dispersion effects. But on the other hand, it also means that they are quite hard to measure. So let's think a bit about how could we measure them. And to do that, we have to first understand what is the effect of a gravitational wave that was generated very far away, but now is passing by a distant observer. And this is illustrated in the left upper plot here, where there's a wave propagating along the direction indicated by the yellow arrow. And we are looking at a slice of space perpendicular to the direction of propagation. And if we take 2 points on this spatial slice that are separated by some distance L, the wave stretches and squeezes the space in such a way that there's a change in the distance between the 2 points by an amount delta L. And the fractional change in length is directly proportional to the gravitational wave amplitude. So that indicates that to measure a wave amplitude, we have to look for these changes in length produced by the stretching and squeezing of space as the wave passes by. And just to get ourselves an idea of how large of some changes in length could we expect? Well, if we take a length of the entire Earth, then typical strong sources from astrophysical events like colliding black holes deform the Earth by only about 100,000 times the size of an atom. So it's incredibly small. Just for comparison, so a hair is typically about 0.1 millimeter in size, and an atom is only a millionth of a hair, roughly speaking, and the Earth deforms even much less than an atom. So the effect is really tiny, and also that is a reason why we don't notice gravitational waves, even though they're passing by us all the time. So given that estimate, it might seem completely hopeless that we could ever measure gravitational waves. But there are some very sophisticated experimental techniques that allow one to look for very small changes in length. And this is possible with laser interferometers. So here I'm showing an animation of the basic setup and principle behind this. So a laser source shines a laser beam onto a special crystal, which divides the beam into two beams that go along orthogonal directions, get reflected back by mirrors, and then the two beams recombine. But depending on the relative length in the arms, they combine either destructively or constructively. So you can think of the laser light kind of like waves. So depending on how the crests and troughs line up, they will either cancel each other out or enhance each other. And this leads to a different interference pattern, which is shown now on the screen. You can see as the arm length changes, the interference pattern changes. And changes in the relative length between orthogonal directions are precisely the changes we expect from gravitational waves as they pass by and squeeze and stretch this space in different ways, in different directions. So by looking for changes in the interference pattern, we can measure the effect of the wave within this setup. And at present, the way the setup is done is that when there's no wave present, there's a photodetector that is centered on one of the dark fringes of the interference pattern. So no light reaches it if there's no wave. But then if a wave passes, then some tiny amount of light reaches the photodetector. And nowadays, the photodetectors can be quite sensitive to even small amounts of light. So we can measure gravitational waves. But to do that, it doesn't just take a sensitive photodetector. It takes actually large-scale instruments, or even facilities is a better word, that have been built around the world. There are two detectors in the US called the LIGO detectors, which stands for Laser Interferometer Gravitational Wave Observatories. One is in Washington State, so near the West Coast. The other one is in Louisiana, which is in the south, kind of east of the US. There's also a detector in Italy, near Pisa, called the Virgo detector, and a detector in Japan in the Kamioka mine, which is called KAGRA. And then there's also a small detector in Germany, but the bigger instruments are the LIGO, Virgo, and KAGRA ones. And they have, as you can see indicated on the photos here, they have 4 kilometer long arms or 3 kilometer long arms. So they are really big instruments. And they are quite sensitive to small changes in their arm length. smaller than the size of an atom. And it doesn't take only a large-scale instrument to do that, but also very sophisticated interior design of the instrument. For example, in the left here, you can see this round thing is the mirror that reflects the laser light at the end of the arms. It's a 40-kilogram object, and of course, very highly polished and specially coated to minimize any losses. And these mirrors are then hung on some special strings to shield them from environmental disturbances. And they're hung on a big tower of very sophisticated seismic isolation technology, because if there's a truck passing by or some helicopter flowing above, then that would disturb the detectors. And here the seismic isolation shields it from such disturbances to a large extent. And also, lastly, you can see here the laser system is a much more sophisticated setup. There are all kinds of cavities to enhance the propagation of the light. The beam tubes are, all the 4 kilometers are under ultra high vacuum, because one wants to avoid that the laser interacts with any residual gas particles or so. So it's a very big experimental effort has gone into this. And it also took many, many years for all of this to be realized. So here I'm showing you just a very rough timeline. The history of the field of gravitational waves is actually very interesting, because there were many different types of developments. But I'm not going to go into all of this here. Just to give you some milestones, already soon after Einstein published his theory of general relativity, he realized that one of the consequences is the existence of gravitational waves. And he already estimated that the effect would be really small. And then later on, he and others in the community came to doubt about the physical nature of the gravitational waves, because the theory is mathematically so complicated and has many spurious or so-called gauge degrees of freedom, that it's sometimes difficult to see what are the physical consequences of a calculation and what are actual physical effects compared to just mathematical artifacts. Anyway, in 1994, the construction of the initial LIGO detectors began finally, after also some evidence for the existence of gravitational waves by looking for effects in binary pulsars had received a Nobel Prize in Physics in 1993. And people had thought very much about how to best look for these gravitational waves. So the construction began, and it was always the idea that there would be an initial incarnation of all the detectors to demonstrate that they can actually achieve such a high sensitivity to detect gravitational waves. And then in 2010, the detectors were shut off and improved in 10 times in sensitivity. And finally, in 2015, they came online again. And pretty much as soon as they turned on and were almost ready to start the observational science run, some very interesting feature was observed in the detector outputs. You can see that here. The plot is showing you the strain, which is the dimensionless change in length, or fractional change in the arm length, as a function of time. And in both detectors, it looks like there's some kind of wavy signal present, but it turns out if one looks at the frequency of these oscillations, it's exactly the frequency with which the AC power is flowing through the power lines. So that is not a gravitational wave. One has to filter that out. And the remaining data looks pretty much just like noise. But after some further conditioning of the data, which is a process kind of similar when you try to tune into a radio station and you play with the equalizer knobs to try to get the best signal. Doing that then shows that there is clearly a feature in the data that stands out significantly above the average noise. And this you see circled in the lower plot here. And it's the same, or at the same time, and very similar signals in both detectors, even though they are separated by many thousands of kilometers. So that indicates it is probably a real gravitational wave signal from an astrophysical source. And here it is just shown in a bit more detail, so you can see more clearly the structure of the signal. So again, it's the signals in both detectors in the two panels. It still looks a bit ragged because there's still some noise in the detectors. And these kinds of blob-like structures, they are a representation of how much power is in the data at a given frequency versus time. So you see initially at the time it starts not that much power, which means a darker color on the plot. And then it slowly increases in power, and eventually the high, very bright region, which also coincides with the largest wave amplitude, that it has the largest power. And this characteristic sweeping up of the frequency and the power, this is called a chirp, and it is characteristic of a binary black hole coalescence. So what was this signal? Well, some further data analysis revealed that it was two about 30 solar mass black holes, so extremely massive objects, but because they're black holes, they were actually quite small. So here on the map, they're drawn to scale. So they were not bigger than the size of the Netherlands, for example. And they were moving extremely fast. And initially, what is drawn also on the map to scale is the orbital separation they had when the signal was first picked up by the detectors. So they were orbiting already at close to the speed of light. And that was distorting the space-time curvature. And that takes energy to make these distortions and produce gravitational waves. So the orbit slowly shrinks. And you see on the very bottom, the corresponding gravitational wave signal. So as they are orbiting, they produce these kinds of sinusoidal gravitational waves. And the signals get stronger and also oscillate faster in frequency as the orbit shrinks and the two black holes move faster and faster. Eventually, they are so close that they collide, which is the most dramatic distortion in the space-time curvature. So it produces the largest peak in the gravitational wave signal. And they merge into a single black hole, which is initially perturbed. So there are still, after this peak in the gravitational waves, there are still some oscillations from the final black hole, but eventually it settles down into some equilibrium state, at which point there are no further gravitational waves produced. And we no longer have a way to observe this particular black hole. And if you've been staring at the numbers I've indicated here, so it is true that 29 plus 35 does not add up to 62. Where did these missing two solar masses go? Well, they were actually converted to energy in gravitational waves in the process. So that's a huge amount of energy that was turned into gravitational waves. But by the time the waves reached the Earth, they were just tiny, tiny in amplitude, and we didn't notice them in everyday life. Only the very sensitive LIGO detectors could pick them up. And to better understand all of this process and what was happening to the space-time curvature, I'm showing you here a numerical relativity simulation that was made of this system. So on the bottom, you see an indication of a quantity that kind of tracks the curvature of space-time, not exactly, but it gives an indication. So red means higher curvature regions. And you see on the top the event horizons of the two black holes as they orbit each other. And on the very bottom is the gravitational wave signal. And this was produced by really solving numerically the complicated Einstein field equations for the dynamical space-time of the binary system. So now the movie slows down because they get so close to each other that now a common event horizon engulfs both of these black holes, and they have merged into a single black hole, which now shakes off its perturbations, and all that remains is the gravitational waves traveling outwards. And then for this particular event, about a billion light years later, after they had traveled very large distances through the universe, finally they reached our detectors in 2015. Okay, I'll stop this video here. And now the question is, of course, what can we learn from these signals? And also, how do we actually know this signal that was seen in the data corresponded to a binary black hole system with two roughly 30 solar mass black holes at a distance of 1 billion or even more light years from us? And the answer is the way the analysis is done and information is extracted from the data is by cross-correlating these detector outputs with theoretical predictions. And the theoretical predictions say that the gravitational waves are a characteristic fingerprint of their source. And here you see just a few examples of changing different physical properties of the source and seeing the shape of the waveform change. For example, the first example is two black holes on circular orbits with their spins aligned with the orbital angular momentum. Then mass ratio 1:10 looks more asymmetric. Similarly, if one doesn't have circular orbits, if the spins are not aligned in the same direction, one gets these modulations in the waveform amplitude. If objects are not black holes, but other objects like neutron stars, the waveforms look very different. Similarly, for a neutron star black hole system, it looks yet different. So these are just a few examples. But then the idea is that we have all of these theoretical predictions and we can cross-correlate them with the data to see which of them best matches the data. Of course, it's done in a much more sophisticated way, but that is the basic idea behind it. And since this first event, many more black hole events were observed. And what were their properties? Well, here you see this illustrated in terms of their masses. So all of the blue dots on this diagram are different black holes observed in gravitational waves. And on the y-axis, you see an indication of their masses in terms of solar masses. And you can see they range all the way from just a few solar masses down to over 100 solar masses. So quite a variety of different types of black holes, which is a big step because it's the first time we see all of these merging black holes in the universe. And we learned that actually every few minutes, there is a black hole merger in the universe. And in 2017, there was also the Nobel Prize in Physics given for gravitational waves to Ray Weiss, Kip Thorne, whom was already mentioned in this morning's talk, and Barry Barish. So this is one aspect we can learn about black holes, but there are many more questions that gravitational waves can enable us to address or give us some clues on. Well, with the distribution of masses, one could already see that now it is possible to make a census of the black holes that exist in the universe, at least, yeah, with those accessible to the detectors, and also record their properties and understand better where do they come from, were they formed maybe through some exotic quantum fluctuations in the early universe or from astrophysical channels. What are the different formation channels in astrophysics, how they can form, and how do they evolve and grow, and how do the binary systems of them form? So that can go on and on and on. There are many interesting questions to be addressed.
I have a small question about the previous slide. What
Yes.
Is the meaning of the horizontal separation of the dots here?
That the horizontal has no meaning. It's just a collection of all of the events.
Okay.
To date. But yes, I forgot to say, so the meaning of these vertical ones is always the two lower ones merge into the upper one. So for each event, you see 3 black holes, unless it was an event involving neutron stars where there might be one final black hole or a neutron star and a black hole merging into a black hole.
Okay, thank you.
Okay, yes, please do not hesitate if you have clarification questions to interrupt me, because I also don't keep track of the chat because of the screen sharing. So if there are questions, yeah, don't hesitate to speak up. All right, I will continue on then. So besides all of these demographical questions, there's also, of course, the question, are these black holes the black holes of Einstein's theory of general relativity, or are there maybe some corrections, or are they completely different types of objects? For example, in string theory, there are some indications that in what looks from far away kind of like a black hole is actually a so-called fuzzball, which is a technical term for an object that has, instead of an event horizon, some fuzzy, stringy, quantum-y structure. And in the interior, the space-time at some point ends and there is no singularity. But there are also many, many other possibilities for compact objects that look kind of like black holes, but then when under closer scrutiny, it turns out they are not. And now that we have all of these many binary black hole mergers, we can also ask, what does the data tell us about this? And this was from a paper by the LIGO-Virgo-Kagra collaboration listed here on the bottom. It is the most up-to-date analysis of the published by them. And it asks the question, how much does a quantity characterizing the final black hole deviate from that is expected in Einstein's theory for a classical black hole? And here, the plot shows the probability density on the y-axis and this extra parameter, which is not so important to know exactly what it is, but just that it characterizes a deviation. So if it's 0, the black hole is a black hole of general relativity. And the red and blue data curves are just results. So GWTC3 and 2 stand for gravitational wave transient catalog 3 and 2. And it's simply a compilation of gravitational wave events after each observing run. So 2 was for an observing run that ended already some time ago, and then 3 was the most recent one. And what is important to note here is also the measurement uncertainty is indicated in gray. And okay, in technical terms, it's a 90% confidence interval. But basically, what you should interpret it as is anything within that measurement uncertainty is consistent with the 0. So you can see basically there are no dramatic differences from GR, but also the measurement uncertainties are quite large. So it's not yet a precision study, but it's a first test basically through this kind of channel. So that's about the nature of black holes. But of course, we can also address many other questions about the nature of gravity itself in the highly nonlinear, dynamical, and strong curvature regimes where it has not been tested before by other experiments. We can also use the black holes as probes for example, physics beyond the standard model or dark matter, which can form clouds around the black hole. And that affects the gravitational wave signal. And also because the gravitational wave signals travel such large distances through the universe to get to us, we can also use them to get some insight into dark energy and the cosmic history of the universe. And maybe one more thing I would like to show you is, so in this paper, Tests of General Relativity, many different kinds of tests have been performed. So testing the final black hole is just one of the many things, because now we want to really closely scrutinize, is everything consistent with general relativity? Do we see hints of some failures or some hints from quantum gravity effects or so? So one more test that was done here is just kind of a null test, which is to subtract our predictions of the waveforms using general relativity from the data and looking for, is there any feature in the residuals that is not consistent with just detector noise? And this was also tested here again. So you do not need to know exactly what the axes represent. The important point here is to know that if the residual is just detector noise, it corresponds to this 45-degree line indicated as the dashed line. And in blue is the results from the analysis of all of the black holes that have been observed so far. And again, in gray is the measurement uncertainty. So again, anything within that uncertainty region is, as far as we can tell, consistent with no large residuals from some channel that is not just detector noise. Of course, the measurement uncertainties here again are quite large. So for the future, we really look forward to doing more higher precision studies. And that also brings me to the future developments, because this year is an exciting year because the detectors are planning to start to take data again. They were shut down also because of the pandemic, actually quite earlier than was initially planned. But hopefully later this year, they can start up again, and they will actually be at much higher sensitivity than before. And here in the plot, you can see what it means for them to improve in sensitivity in terms of the amount of volume of the universe they can observe. And here, this is just illustrated for one of the benchmark binaries. So it's not the absolute volume they can observe, but just you should focus on how it changed for this benchmark case from the initial detectors in 2010 to the first detection in 2015, which is the pink. And then later this year, with the next observing run, they're aiming to be at the orange line. So we really expect a greater number and much greater diversity of events, and also to do higher precision studies on the louder events. So that's very exciting already for later this year, hopefully, or otherwise next year. But there are also already plans to take a big leap forward for the field, because now with these initial detectors, it's basically, the first time we can directly measure gravitational waves from merging black holes. And there are all these interesting new discoveries, but to really do precision physics, we need better instruments. And for the Netherlands, one of the big plans that is especially important is called the Einstein telescope, which is the vision for a next generation detector that would be 10 times more sensitive than the LIGO detectors. And one of the possible sites for it is near Maastricht in the border area between Netherlands, Belgium, and Germany. But it's not yet sure that it will be built there. And it has a triangle configuration, very sophisticated and underground. Lots of sophisticated technology. And to test all of this technology, Pathfinder laboratory was inaugurated in Maastricht just a few months back. And having that instrument would be extremely exciting, because it would measure almost all the stellar mass black hole mergers in pretty much the entire universe. Also many other sources that I did not talk about in this talk, but there would be hundreds of thousands detections per year, and would really enable to do high precision studies, at least for some of the events, and really get the full census of black holes of stellar mass in the universe. And there's a concurrent plan to have a detector in space. And that might sound a bit futuristic to you, but this is actually already quite well underway. It is an ESA-led mission. NASA is also involved, and it's scheduled for launch in 2034. And it consists of 3 satellites separated by more than 1 million kilometers, and already had a Pathfinder mission, which was one of the satellites. And that was exceedingly successful, greatly exceeded any expectations. And the reason we want this detector in space is because it is sensitive to sources with very different frequencies that emit gravitational waves in a very different band. So completely complementary to any sources that ground-based detectors can observe. For example, this detector would see merging supermassive black holes, which exist in galactic centers, throughout cosmic time. And some of these signals would be hugely loud. So again, enable high precision studies. And also another source involving black holes for this detector is a stellar mass black hole spiraling into one of these supermassive black holes. And what you see here illustrated in the right is the lines trace the orbit of the small black hole. So you see it looks quite intriguing, and it really samples the space-time around the big black hole in exquisite detail, for example. So definitely an exciting future ahead. And that brings me to the conclusion. So gravitational waves are finally now available as a new tool for science that give us access to otherwise dark sectors of the universe. And so far, they've already allowed us to do completely new tests of gravity and black holes, and also much more that I didn't touch upon. And also, of course, when taken together with traditional electromagnetic information, one can learn much more about a source than from gravitational waves alone, at least in some cases. And as I mentioned, what we have learned in the past years was already many exciting discoveries, but it's only a first step in exploring all of the gravitational wave sources in the universe. And for that, already the next kinds of detectors are being planned. So many exciting prospects for the future. And I'm now happy to take any questions.
Thank you very much, Tanja. It must be super exciting to work at this field at the moment with these developments happening as we speak.
Yes.
That's amazing. Thank you so much. It was a very clear talk to me, good to follow and very exciting. And it has also generated some questions. I want to start from the top, and I'm going to ask Alan to actually explain his question a little bit. It was the question, how would we notice such a wave of larger amplitude? Quite a technical one, so maybe he can explain what exactly he refers to.
No, it's not technical at all. I noticed a few times it was said that the waves are so tiny and therefore we don't notice them. So it got me wondering, if the waves would have an amplitude of, say, like a meter or something, how would we as humans experience such a gravitational wave?
Yes, so then one would have to go back to the thinking about the general effect of the gravitational wave, which is that it really stretches and squeezes the space. Yeah, so it would also stretch and squeeze us, basically.
Yes, that would be weird.
Yes. So we don't want to be too close to a really strong source, but I don't think we have to worry.
Thank you. That was an interesting idea that a wave that big would pass through us. So the next question is by Johan, and actually Klaas Landsman answered this partially, but maybe you can have your thoughts on it too. Do single black holes generate gravitational waves as well?
Well, only if they are perturbed. So, for example, if something falls into them and causes them to oscillate, for example. I don't know what Klaas said about it. Maybe he had some other insights. But when they are just sitting there by themselves in isolation, they don't generate gravitational waves.
Yeah, so if I may, what I answered is that after gravitational collapse, on the way to the stationary end state of a Kerr or rotating black hole, the collapsing black hole will, I guess, emit gravitational waves, and that indeed is the way to reach this final Kerr state. And there is a conjecture by Penrose.
All the way.
Oh, Klaas, your sound has suddenly gone.
Klaas is gone.
Klaas himself is there, at least half of his head. But maybe as Klaas fixes this, we answer another question. Klaas, can you say something? Strange. No, then we'll I'm very curious about Klaas' answer, but just not to waste time. There are two questions by Luc. And yeah, again, I find them a bit technical, so maybe Luc can explain his questions.
Okay, thanks, Rogier. Yeah, my question is actually, if I look at this slide, there is a very simple function to represent the strain of space that is actually observed in a gravitational wave detector, whereas the configuration of black holes can be quite complicated. So I was wondering about the many-to-one nature of the configuration of black holes versus the signal that is observed. And if it's many-to-one, how to address the inverse problem, where you want to infer parameters of the physical system.
Yes, that's a very good question. So I think this goes back also to what I showed about the theoretical predictions here, how they can change, or how the waveforms can change when changing the parameters of the system. And yes, it is true. So when one looks at the waveforms, they look exceedingly simple. but to really map them to the source properties requires an extremely complicated mapping by going through the highly nonlinear Einstein field equations and solving them for the really dynamical space-time of the binary system. So it is in some sense a bit deceptively, especially these circular orbit waveforms, they look really simple, but to get from them to the black hole system is quite a complicated mapping.
But can you say it's many to one, or because these signals are obtained, I guess, from numerical calculations, right? So how can you be sure that you capture all the kind of variations that you need? And
yeah, so these predictions are obtained from combining some results from the numerical simulations with also analytical approximations and results. So, for example, when the two black holes are at large distances from each other, one can use the post-Newtonian approximation, which was already mentioned this morning when the Einstein-Infeld-Hoffmann paper was mentioned. They already did a first approximation of two bodies at large distances, and one can carry that out to higher order and get an idea of what happens when the two black holes are at large distances. One can also solve for the perturbations of the final black hole, and also perturbatively with a different type of approximation method. And then one has maybe several hundreds or so of numerical simulations that kind of where one can make a model of how to interpolate between these two perturbative regimes. And using all of these methods combined, one can really think about what are physical effects that could impact the gravitational waves. And then, yeah, also what input, I mean, because from the numerical simulations, it's also, they're quite complicated, and it's also sometimes difficult to interpret the numerical output. So taking everything together allows us to make these theoretical predictions. But you're right, then, of course, the effort in the field has gone on for many years and added many more effects. But it is not guaranteed that this gives the full answer, especially for systems outside of the parameter ranges that have been observed. So it's always a caveat that there are also modeling uncertainties.
Okay, thank you. It's clear.
I see another question, and it's by Marcel Roggeband. It's, well, how does the binary model, so with two objects, relate to the ring model of a black hole by the previous speaker? So Klaas talked about how the singularity in a black hole is actually ring-shaped. And the question is about the relation between these.
Yes, so the binary model really focuses on the macroscopic two-body system. So it is, each black hole has their singularity and horizon, and they are undergoing some orbital motion in some sense. And so in that case, yeah, the gravitational waves are really generated mainly by the orbital motion, and then at the merger, a common event horizon engulfs a lot of the space-time, very close to the individual horizons. So I don't see a direct relation between the two quantities.
Thank you. So I have a question myself also. It's about all these events happening. I don't know, maybe you mentioned it, but my first question is really, how far apart are they usually? And then I was wondering, because you see sort of the amplitude increases until something goes wrong, you know, until they merge or explode or whatever happens. So I just wonder how common that is, and from what point onwards you start measuring these amplitudes. From one point onward, they're big enough for you to see them with these LIGO and other setups.
Yes. So yes, it's true that the LIGO detectors, they have some noise that, just despite the best efforts on the experimental side, can just not be mitigated any further. So it's a bit tricky because the data analysis methods actually they integrate the waveforms against the data over a larger stretch of time. So they can even dig out these kinds of signals inside the noise, even if the amplitude is not clearly standing out above the noise, as was the case in this first event. So this is simply a consequence of the fact that the shape of these waveforms is very different from just random noise. So if one integrates over time, one can build up more signal to noise ratio when one cross correlates these signals with the data. But it is true, roughly speaking, the amplitude of the signal has to be large enough to be above the noise floor.
And then my other question was, for how far apart are these things usually? How long? Because you said when they first switched on LIGO with the when it was strong enough, then bam, they found something. But how lucky was that?
Yes, that was quite lucky. Also, it was a really loud signal, which at the time it seemed it was almost too lucky. So there was a lot of investigation. I mean, it took until February of the following year, so several months, to be announced, because there was so much, it seemed too good to be true. So people were investigating, was it maybe some malicious injection or so to fool all the physicists and so on. But it seemed to have been a real signal. And then since there were so many afterwards, it seems entirely consistent. So in the last observing run, there was roughly speaking about one event per week. And so in the first observing run, there were, I think, just a few over several months. So, but as the detectors get more sensitive, they see more and more frequently. For example, with the Einstein telescope, one would just constantly have some signal in the detector.
Mm-hmm. And so, I should pass on some other questions, but my final, just a yes or no, is this in line with the predictions of how often we should see such events?
Well, the predictions of how often we should see such events come from really astrophysics. And there are so many uncertainties because one has to know how often do black holes form, how often do they form binaries, and then are the binaries close enough to merge within the time of gravitational wave emission and so on. And there are huge uncertainties. So it's more the other way around, that now that we know how often LIGO sees gravitational waves from merging black holes, one constrains all of the unknown astrophysics.
Great, thanks. So there are two more questions here in the chat. Is it possible for multiple gravitational waves to interfere with one another and thus create an interference pattern, like with light waves? It's a question from Robin.
That I've not thought about this so much. I would have to think a bit more about this. It's definitely not so common. So the gravitational waves can definitely get gravitationally lensed, for example. But I think interference is not expected to happen, so at least not in most situations, but I really have to think about it more.
Yeah, well, we're still here for another hour, but maybe when you say you want to think, you want to think a bit longer. There's another question. How do different apparatus combine to find the direction in space of black holes? The question by Tom.
Sorry, how does what combine?
Okay, maybe Tom can clarify the question. It must actually also be the last question, I'm afraid.
Well, I hope you understand me, but you also have a direction in space. You know in which direction to find the black hole. And you cannot do that, I think, with a single apparatus. You need at least 3. I don't know whether I'm right or not.
Yes, that is, it's almost true, yes. So that is also one of the reasons why there are all these detectors in different parts of the world to better help localize the source on the sky where it came from. And this is simply done by kind of triangulation, because with just one detector, there are still some degenerate directions of where in the sky the source could have come from. Yes, this is why another reason why we need many detectors around the world to better localize the source.
Thank you.
Well, thank you so much, Tanja, for this excellent talk, and thanks again also for carefully answering all the questions. It's been a joy to have you here and to listen to it.